So we have a problem where I've kind of jotted down the information about the problem initially, but I can explain it again. The situation is that we have a rocket here, and this rocket is on a launch pad, and it's about to blast off. And what we're trying to find about this rocket is what is the thrust force of the rocket. Now we can assume, we have to assume this, by the way, we have to assume that the rocket has uniform acceleration. And the reason why I make a point of this is because in reality rockets do not have uniform acceleration, because their mass is continually changing, because most of their mass is made up of fuel, and as they rise they lose fuel. And so if you have a changing mass, chances are you're not going to have uniform acceleration. So for whatever reason, maybe this is a special type of a rocket, maybe perhaps it's using something else, but whatever the case, in order for us to be able to solve this, we're going to assume the mass is 158 kilograms, and that's a constant mass. Now, the rocket basically rises 725 meters, so about almost, 3/4 of a kilometer, and it takes about 8.6 seconds to accomplish that. The question is, what is the thrust force on the rocket? What we got to do here is we have to draw the free body diagram of the rocket. Now I'm going to use a different color here for the force vectors. Don't be fooled into drawing a thrust force down because you see flames coming out the back side of the rocket. That's wrong. Okay? The thrust force of the rocket pushes the rocket up. If it didn't, at blast off, the rocket would smash into the ground. Not good. But there is another force acting on the rocket. Remember the magic sentence. It says, what's touching it plus gravity. Now in this case, that what's touching it doesn't really account for the thrust force. Although the thrust force is a result of throwing fuel at a very fast velocity in the opposite direction. So the rocket is throwing fuel down, and that results in a thrust force up. But my point of mentioning the magic sentence is, don't forget about gravity. Many people forget gravity in this situation, and of course we have to assume when we say it's on a launch pad or when it's on the ground, we have to assume, although it's implied, that it's blasting off from the Earth. After all, we're not going to assume another planet. So, therefore, if it's on the Earth, there is gravity going down. So let's now do the sum of the forces. Let's do this in a black. Sum of the forces is equal to F net. Now I'm going to take up as being positive. You don't have to. It's not mandatory. But it is convenient. After all, it will give us a positive for our height. So if I say up is positive, that means F thrust is positive and gravity, being mg, is negative because it's down. Now realize that, of course, this does mean summation. I'm simply adding a negative. Adding a negative is like subtracting a positive. It's the same thing. So now I can say, all right, well, that's equal to F net, but F net is ma. And so we can now solve. Well, we can't really solve for A yet. But you see, here's the thing, is that there's a world over here, and there is a world over here. And this is dynamics, and this is kinematics. And they are connected by a bridge, and that bridge is acceleration. So this acceleration is what is going to connect us to the two. Now, if we think about what we're given in the problem, look at this. A height and a time. That's a kinematics problem. Let's figure out if we can determine the acceleration of that kinematics problem. So let's move it over here, and let's take a look at this equation. Delta D equals 1/2 AT squared plus VIT. Now, the initial velocity of the rocket on the launch pad, here's another assumption that you have to kind of make, is that when it's sitting here on the launch pad, the initial velocity is 0 before it blasts off. So, if that's true, this term disappears. And we're looking here for the acceleration, because that's what's going to connect us to dynamics. Let's solve for the acceleration in this equation algebraically. A equals, take the 2, multiply it by the delta D, take the t squared, and divide by it. So we're left with 2 times, now what's the distance? 725 divided by, and what was the time? 8.6 seconds. So we go 8.6 seconds squared. And we're going to get, let me take out my trusty calculator, and we'll go to enter 725 times 8.6 squared divided by. And we're going to get an acceleration of 19.6. So this is pretty much approximately, 2 G's. That's a decent acceleration. This is obviously meters per second squared. Now, once we have the acceleration, look at this equation here that we solved. What are we looking for? What's the purpose of this problem? The purpose was to find, right here, to find the thrust force. So I am going to rewrite this equation here to solve for the thrust force. And when I do that, I'm going to get the thrust force is equal to ma plus mg. You see that? So take this term to the other side, and it becomes a plus. And in fact, now I can even simplify it even further. I can factor out the m, and I can go a plus g, and that's even easier. Nice. And everything's solved already. I have a, and I have m. M was given to me in the problem. It was right here, 158 kilos. So I'm just going to go 158 kilograms multiplied by the acceleration of 19.6 meters per second squared plus 9.8 meters per second squared for gravity. And if I do that, I go 9.8 plus, and then I go 158 times, and I end up with a thrust force that is equal to 4,646 newtons. Or I can say 4.6 kilonewtons. So that's the required thrust force of the rocket. We've solved the problem. Hope you enjoyed it. See you next time.